about efficiently contractible maps.
OK, thanks very much for having me. It's neat to be here. So this year, one of my kind of favorite questions in geometry got resolved, and so I'm going to tell you about it. It's work done by Greg Chambers and Dominic Dotterer, Fedor Manin, Steve Ferry, and Shmuel Weinberger. And maybe I'll start by stating the theorem and then give a little bit of background and history. So here's the setup. Suppose we have a map from the M sphere to the N sphere, and it's a contractible map. And it's not too geometrically complicated. So the way we'll measure that is that the Lipschitz constant of the map is some number L. And then, so it's contractible, so there's a null homotopy of this map. But the problem is to understand how geometrically complicated the null homotopy has to be, and in terms of its Lipschitz constant. So here's the theorem. Then there exists a null homotopy, H. So H is a map from the M+1 ball to Sn. It's a null homotopy, so H restricted to the boundary is our map F. And the Lipschitz constant of H is not too much bigger than this L. So it's bounded by some constant times L if n is odd. And it's bounded by some constant times L squared if n is even. So the other thing I wanted to say at the beginning is that, so this is a wide, broad geometry conference. So this talk is meant to be understandable from the beginning to the end to all geometers. So at any point, if it's not, let me know. And also, I'm trying to give a board talk in a big room. So if it's too small or too squiggly or too messy, let me know. Questions about the theorem? OK. So let me give you a little bit of background and history. So this was a question that was posed by Gromov in the 90s. And he thought about it, and he proved the following estimate. He proved that there's a homotopy, H, and the Lipschitz constant of H is bounded by exp of L. And the number of exponentials in this tower of exponentials depends on m and n. So he sketched a proof of this in something that he wrote. To be honest, I don't understand every detail of this proof, but I can tell you the kind of spirit of it. So the spirit of it is to take some of the tools in algebraic topology that are useful for studying the homotopy groups of spheres or figuring out if a map is contractible. And so things like spectral sequences and fibrations. And so he took a proof that some map is contractible using those things. And he unwound the proof. And inside of the proof, it actually does implicitly construct a contraction. And that's the Lipschitz constant of the contraction, which is implicitly described in the traditional proof. OK. And you can see that it's much bigger than the actual truth. And a bunch of people thought about it. I thought about this problem several times, and I just felt like I never knew how to get started on it. And so I think it's exciting that they figured it out. And not only that, but the proof that they figured out is not that complicated. So I can explain to you a good bit of it. So the goal for today is to do a pretty full sketch of the proof in the odd case. Also, there are some cases that are easier. Like if m is smaller than n, it's not that hard to prove this. And if m is equal to n, it's a little harder, but not that hard. So I'm going to focus on what's really the hard case, which is when m is bigger than n. And when m is much bigger than n, that's when this tower of exponentials is very long. OK. Let's see. So before we start, I'd like to mention two key tools. So this work it's kind of on the interface between geometry and topology. So there are going to be one key tool from topology and one key tool from geometry, and we'll see how they work together. So the key tool from topology is a theorem of Serre from the 50s. And Serre figured out which homotopy groups of spheres are finite and which ones are infinite. And a remarkable thing is that sort of almost all of them are finite. So here's the theorem. If you look at pi I of Sn, they're almost all finite, except for a couple of cases. The first case is pi n of Sn, which is z. And the second case is it only happens if n is even. And then if n is even, pi 2n minus 1 of Sn is z plus something finite. Okay. So this is responsible for the difference between even and odd in the statement of the theorem. In the odd case, there's only, if n is odd, only one of the homotopy groups of Sn is infinite. It's pi n of Sn. And the even case is a little bit more complicated. Maybe it's also maybe worth mentioning that it's not known whether this is sharp. So the only lower bound, there's a trivial lower bound for the Lipschitz constant of h, which is L, because the restriction of h to the boundary is f, which has Lipschitz constant L. That's the only interesting lower bound that I'm aware of. It's the only lower bound that I'm aware of. It's not interesting. And Gromov conjectured originally that it could be L in general. But on the other hand, looking at their proof, I think it's natural enough that maybe this will turn out to be the right answer. Okay. So coming back to what we learned about the homotopy groups of spheres, they're almost all finite. And the ones that are infinite have a very geometric description. So this is the degree. And this here is the Hopf invariant. And both of them can be described in geometric terms, say using differential forms. So when we look at homotopy groups of spheres, we see either things which are finite, and that's going to be good for us for one reason, we'll see, or things that have a very geometric description that we can get our hands on using things we know from differential geometry. Okay, so that's one key tool. And the other key tool has to do with the isoparametric inequality. So I'll call it the Federer-Fleming approach to the isoparametric inequality. So coming back to our theorem, this theorem looks like a kind of cousin of the isoparametric inequality. It compares some size of something that's happening on the sphere, on the boundary of the ball, with some size of what's happening on the interior of the ball. So it's like I think of it as a kind of inventive cousin of the isoparametric inequality. And we'll see in the proof that somewhere underneath this, somewhere to help attack this, is the classical, more or less classical isoparametric inequality. So I'll remind people of one of the things that Federer and Fleming proved to give a flavor, make sure people have some flavor of what this means. So one of the things they proved is that if Z is a K-cycle in the n sphere, or in the m sphere, let's say, then there's a chain Y that it bounds. So the boundary of Y is Z. And the volume of Y is bounded by some dimensional constant times the volume of Z. Okay. Although for full disclosure, we won't exactly be using this theorem. What we're going to be using is Federer and Fleming's idea about how to prove this theorem. Okay. So these are the two things that go into the proof. So the goal of the talk is we're going to outline the proof and see how this ingredient from homotopy theory and this ingredient from differential geometry can get used to construct H. Yeah?
You take advantage of the power in the isoparametric inequality?
Right, so the question is, we could say something better here. Or we could say volume K of Z to the K plus 1 over K. And so comparing the two options, this lower one is better if z is small. And actually, the upper one is better if z is large. Now, we won't literally be using either of them, but the one we would more or less would be using was the one for large z. Other questions or comments? OK, so let's start to talk about the proof. So I'd like to think of both of my spaces as triangulated. So for Sn over here, I'm going to visualize Sn as the boundary of an n+1 simplex. Sn is the boundary of the n+1 simplex. OK, and over here is the m+1 ball. And I'm going to triangulate it. So the m+1 ball is the interior here. The m sphere is there. And I'm going to triangulate it. So here's a little piece of the triangulation. And it goes on inside. And it's a fine triangulation. I'll call it tri. And it has edge length approximately 1 over L. And that scale is adapted to the fact that my map F on the boundary has Lipschitz constant L. So here's what I'm given. I'm given a map F from the M sphere to the N sphere, which has Lipschitz constant L. And I'm told that it's contractible. So I might as well be given some contraction. I'll call it little h, which goes from the ball to Sn. But this one has no geometric bounds. This is a geometrically terrible contraction. So I'm given this, and I want to kind of upgrade this little h to a big H with a nice estimate on its Lipschitz constant. OK. Now this, having Lipschitz constant F equal to L on the boundary is very similar to saying that F is simplicial. Right. So let me remind you what simplicial means. Simplicial means that if I take two of the vertices on the boundary, then, so first of all, each vertex on the boundary should be mapped to some vertex of the sphere. And each edge on the boundary should be mapped to an edge on the sphere. Or it could happen that these two vertices go to the same vertex, and that edge just goes to the vertex as well. So that's simplicial. OK, now why do I say this? Maybe I'll say this for a second. So it's easy to see that if F is simplicial, then its Lipschitz constant is around L, because each little edge here of size 1 over L is stretched to a big edge of size 1, but nothing worse than that. And that's Lipschitz constant L. And it's actually not that hard to see. It's not that hard to go the other way. So if you have a map of Lipschitz constant L, it's not that hard to approximate it with a simplicial map. So without too much loss of generality, we can imagine that our F is simplicial. OK. So that's what's going on the boundary. On the other hand, on the inside, life is different. So if I take two vertices on the inside, so first of all, they may not be mapped to vertices. So maybe they're mapped here and here. That's not such a big deal. But also, I have no control at all on what happens to the edge between them. So this map on the edge may be very long and wiggly. It can go around the back there, around the back there, back up here, something like that. And it really can be much worse than that. I remember going to talks with Misha where he liked to put his chalk on the board and do something like this, which I was tempted to do, but somehow with this 3D picture, I thought it would be incomprehensible. But that's what you should imagine is happening on the edges. OK, so the first thing we're going to try to do, so what we're going to try to do is to start with this map little h and gradually tighten it up, straighten it out, until it becomes a reasonable geometric map. And we're going to try to do it one skeleton at a time. So first we're going to try we're going to arrange that the vertices actually go to vertices instead of being in the middle of faces. That's not that hard. And then we're going to try to tighten up the edges so that they're not going crazy, and so on. OK, so let me state a lemma. Lemma for j starting at 0 and going up to n minus 1, there exists some map hj so that hj agrees with f on the boundary. And if I take hj and I restrict it to the j skeleton of the triangulation, this is simplish. OK, so proof sketch. So j equals 0 is pretty easy. In other words, I'd like to homotope my map so that the vertices, instead of being mapped here, get mapped to other vertices. It's not that hard to do that. So let me explain j equals 1, which is sort of the typical case. Let's explain j equals 1. So, I'm going to pick an edge, E. So here's E. And let's think about what happened to E under the map H0. So H0 did successfully map the vertices of this edge to some vertices. And the edge itself, it did something crazy with. OK. But any two paths from here to here are homotopic on the sphere. Let's imagine n is bigger than 1, an interesting case. So if I take H0 restricted to E is homotopic to just a straight edge. Maybe in yellow. OK. I do that for every edge. So it means that if I take H0 restricted to the one skeleton of the triangulation, this is homotopic to a simplicial map called H1. Cool. OK, so I figured out how to define H1 on the one skeleton. And it's a homotopy. So I'd start with H0 on the one skeleton, and I homotope it to a better map. And I can extend that homotopy to the whole space. To the whole Bm plus 1. And that gives me H1. OK. So let me ask, can people read down here to the bottom of the board? Yeah. OK. And does anyone want to be reminded about how to extend a homotopy, the homotopy extension lemma? OK. OK. So that's how to get H1. And the same thing works all the way up to Hn minus 1. And then it stops working. So let me explain where we run into a problem. Okay, so there's a problem at the end skeleton. So here we have, I'll draw over here an n face. This is delta n, an n face. And we have a map Hn minus 1, which behaves nicely on the n minus 1 skeleton, so on the boundary of that face. So here's Sn. And so the boundary of our face is mapped in some nice simplicial way into Sn. But the problem is that if I take the map I have so far and I restrict it to delta n, it might not be homotopic to the simplicial map that takes delta n to this face. Because, for example, instead of going on the front face of Sn, it might go and wrap around the back of Sn. And now it's in the wrong homotopy class. Right? And it might do worse than that. It can wrap many times around Sn. OK. OK. So we need to say this in a more precise way so that we can talk about how to fix it. So here's how to say it. OK, so I make a definition. Let's say that d volume Sn is a normalized n form on Sn. So meaning, if I integrate over Sn, d volume of Sn, I get 1. And now I define alpha. So for any map H, alpha sub H of an n face is the integral over the n face of the pullback of d volume of Sn. So this measures, in some sense, how many times this n face has been wrapped around the target Sn. OK. And what sort of object is alpha h? Well, alpha h takes each n face of my triangulation, and it spits out a real number. So it is a n cochain of my triangulation with values in R. OK. And now I can say the problem that I said colloquially over there, I can say it more precisely. The problem that I'm worried about is that I have no bound, no control for the size of alpha h of a simplex. OK. So this is the most important problem. There are two important problems. I said at the beginning there were two key ideas, two key tools, one coming from topology and one coming from geometry. This is the one that we'll solve using the geometry. And let me just state for now the solution. So lemma, that was lemma 1. This could be lemma 2. There exists a map hn minus 1 tilde. All right, so that it does the good things it did before. Hn minus 1 tilde is equal to f on the boundary. And hn minus 1 tilde is simplicial on the n minus 1 skeleton. And in fact, it's even the same as hn minus 1 on the n minus 1 skeleton. Right? And this thing is under control. Alpha hn minus 1 tilde is always small. Okay. So I just stated that there's some way to rig this n minus first step where actually these wrapping numbers are all bounded. And we'll come back to the proof of this. Come back to the proof. And it uses the Federer-Fleming stuff. OK. But in terms of the organization of the lecture, I think it's helpful now to go on from here and finish constructing capital H. OK. Cool. So coming back to this picture, for hn minus 1 tilde, it still may not be the case that hn minus 1 tilde maps this simplex to the homotopy class that is of the simplicial map. It could go around the back or something like that. But it doesn't do anything terrible. And so we're going to use that to extend, to straighten out our map on the n skeleton. So there's this. So we have, using that, we get a map Hn, which is f on the boundary. And Hn on the n skeleton is constant L Lipschitz. And actually, even better than that, there are only order of 1 choices, possibilities, for the behavior of Hn on an n simplex. Yeah. So how do we do this? I look at an n simplex. The boundary has been mapped simplicity onto Sn. There are only finitely many ways that could have happened. And then there's this wrapping number, this homotopy invariant. But there's only boundedly many choices for what it could be. And for each of those, I pick some way to fill in, to extend my map to delta n. There's finitely many choices. And so that's it. Now I've extended to the n skeleton. And because there are only finitely many choices, the Lipschitz constant only gets bigger by some constant factor. Questions or comments? OK. OK, so now let's try to go on. If we try to make Hn plus 1, actually the story is similar. So to make Hn plus 1, so now I want to go further and try to do something good on the n plus 1 skeleton. If I take Hn and I restrict it to the boundary of an n plus 1 simplex, there are only order of 1 choices. Right. And they're each CL Lipschitz. And then if I take Hn and I restrict it to the whole simplex, there are only order of 1 relative homotopy classes because of the Serre theorem. So the number of homotopy classes of ways to extend the map from the boundary to the whole n plus 1 simplex is isomorphic to pi n plus 1 of Sn, which is finite. That particular one was known before Serre. So there are only finitely many ways to extend it. And for each option here and each option here, we pick some way to fill in our map on the n plus 1 skeleton. And so we get, there's Hn plus 1, which is equal to f on the boundary, and Hn plus 1 restricted to the n plus 1 skeleton is CL Lipschitz, and order of 1 choices for Hn plus 1 restricted to an n plus 1 set. Cool. OK. And then we just keep doing this. And our final homotopy is when we get up to the m plus 1 skeleton. In other words, the whole space. So this is CL Lipschitz. Yeah, good question. Right. Right. OK, so I want to define Hn plus 1. And so I pick an n plus 1 simplex, and I want to figure out how to define it. So the first thing I do is I look at Hn on the boundary of the simplex. And Hn plus 1 is going to agree with Hn on the boundary of the simplex. And there are only finitely many choices for what it could be doing. And then I look at Hn on the interior. And I'm going to change Hn on the interior. But I'm going to change it by a homotopy. And so I just look at its homotopy class. There's only finitely many choices of that. So there are actually only finitely many possibilities that I have to look at. Yeah, okay, so I'm using this finiteness to cover the fact that I have no intelligent idea about how to pick hn plus 1. But there are finitely many possibilities that I run into. For each one, I write down a way to extend it. And so each of those extensions has a Lipschitz constant, but there's only finitely many of them, so it has a finite maximum. And that's where I get this. Yeah. Cool. Another question you might ask is, why do I want to pick the extension in, yeah, why don't I write on the board a little better? So hn plus 1 restricted to the boundary of the n plus 1 simplex is just the same as hn restricted to the boundary. And then hn plus 1 restricted to the simplex is not the same, but it is relatively homotopic to hn plus 1 on the simplex. Now, why do I want to do this? Then, since this is a relative homotopy, I can use the homotopy extension theorem, or lemma. To define hn plus 1 elsewhere. So that's why I need to have this relatively homotopic. OK, thanks. That is hn. Thank you. Yeah. Good. Good. OK. So the first key observation is that because of Serre's theorem on the finiteness of homotopy groups of spheres, we can do this rather soft construction of capital H as soon as we get over this one tricky moment where we can't use that argument because this thing could have been arbitrarily big. And if we were in even dimensions, we would eventually hit another tricky moment, if n was even, where there would be not order of 1, but infinitely many homotopy classes here, and we would have to again think. OK. Cool. So the plan for the rest of the talk is to talk about this lemma and see how this reduces to geometric things. It reduces to something in the spirit of the isoparametric inequality. OK. OK, so we're going to talk about this lemma. Let me first abbreviate G for hn minus 1 so that I don't have to carry these subscripts. And the first observation that I want to make is that if I take alpha g of a simplex on the boundary, so if the simplex is in the boundary, this is bounded by 1. Actually, this is just less than or equal to 1, because G is a simplicial map on the boundary, so that simplex is just one of the faces of Sn, and its volume is less than 1. OK. Observation 2. This alpha G is a cocycle. So proof, what I have to check is that if I take alpha G and evaluate it on the boundary of a simplex of 1 dimension higher, I have to check that that's 0. That's the integral over the boundary of this simplex of G pullback of d volume of Sn. In other words, that's the degree of the map G from the boundary of the simplex to Sn. And that's 0 because the degree is 0 because G extends to the whole simplex. OK. So this object, alpha sub h or alpha sub g, it's a cocycle. Now, what can I do with it? what can I do to my map in order to change, when I go from h to h tilde, what kind of changes can I hope to make in this cocycle to improve it? OK. So observation 3, we can choose G tilde to arrange that the new cocycle, alpha of G tilde, is the old cocycle plus the co-boundary of beta, where beta, so for any beta, which is an n-1 dimensional cochain with integer coefficients and vanishing on the boundary. And the reason for vanishing on the boundary is that this G tilde is supposed to be equal to G on the boundary, because all of our maps are equal to F on the boundary. OK. So why is that? Let's erase here. OK. So in the triangulation, I'm going to pick out a particular n-1 face. So I'll call this B. It's an n-1 face. And it's part of a bunch of different n faces. So I'll draw in some of them. Yeah. So that n-1 face is in the boundary of several n faces. And then the original map, G, is mapping this thing to Sn. And this n-1 face goes somewhere. It's simplicial, so it goes to a nice place. And what I'm going to do, basically, is to modify G by fixing the boundary here, but now taking this edge and wrapping it all the way around Sn till I get back where I started. So in words, I'll have capital G goes from Bm plus 1 cross 0, 1 to Sn. Capital G at time 0 is little g. Capital G at time 1 is a new map, little g1. And if I take capital G on this edge cross 0, 1, it has degree 1. And if I take capital G of xt is just little g of x on a whole bunch of places. So for x in the boundary, or for x in the n-2 skeleton. So this boundary, so G is not changing at this boundary, but it is changing along this n-1 face, and it's changing by, over time, gradually wrapping around and coming back and closing up. Yeah. OK, so how does that affect alpha? Maybe it helps to visualize this n face here. So that n face is mapped somewhere nice. And this part in here, maybe if we were lucky, might have gone there. It might have also gone around in a more complicated way. And now when I do this homotopy, I leave this part of the triangle fixed. And I take this green edge, and I start to stretch it out. And this face stretches. And I wrap the green edge all the way around the sphere until I come back where I started. And it changes the alpha value on this face by 1 when I do that. So algebraically, the conclusion is that if I take alpha of G1, it's alpha of G plus the co-boundary of capital B, where capital B is the n-1 chain, which is 1 on capital B and 0 on other n-1 faces. Take a little pause. This was, I think, one of the trickiest things to explain. I spent a while trying to figure out how to draw it this morning. Does that make sense to people? It takes a lot of courage to ask a question in a big room like this. OK, good enough. OK, and that's observation 3. So if I take any integer co-boundary beta, I just repeat this operation a bunch of times where I take different n-1 faces b. And if b is weighted with weight 3, I wrap it 3 times around S. Okay. So that's all there is to this. OK. So now I want to figure out how to pick this beta. And so observation 4. Yeah. So observation 4 says if alpha bar is any cocycle on my triangulation, real values, and it agrees with alpha on the boundary. So then, because the relative cohomology group is 0, alpha bar is automatically alpha plus a coboundary of beta bar. But beta bar is not integer. It's an n-1 cochain with real values. OK. So I'm only allowed to take alpha plus delta beta where beta is an integer, but I can kind of round this thing off. So I can choose beta, which is integral, that is close to beta bar. So that if I take the difference between beta and beta bar on a simplex, it's always smaller than 1. And then if I take alpha plus delta beta, and I evaluate that on a simplex, it's almost the same as alpha bar. So it's less than alpha bar on the simplex, plus the effect of this rounding. But if I look at delta beta on an n simplex, it has n plus 1 faces, and on each face I have a rounding error of size 1. So here, an error of n plus 1. OK. So therefore, we only really have to find this alpha bar. We have a problem, a cocycle extension problem. We have a cocycle on the boundary, which is small, and we just need to extend it to a small cocycle on the whole ball. So let me write that down. Extension lemma, cocycles. So if alpha is a cocycle on the sphere, and let me say that m is bigger than n here, then there exists alpha bar, a cocycle on the ball, so that it's an extension, and it's not too much bigger. Cool. So this extension lemma lets us find a good alpha bar. And then we carry out observation 4 and go through. And that's how we find our way of modifying our map at the n-1 skeleton. Now, a cocycle is a lot like a differential form. So this is similar to an extension lemma you could state for differential forms. So this says that if omega is a closed n form on Sn, m is bigger than n, then there's a nice extension. There exists omega bar, a closed n form on the ball. And so omega bar equals omega on the boundary and with a bound, omega bar L infinity is not much bigger than omega. Cool. OK, and this inequality about differential forms. So first of all, I think this is a natural thing in its own right that probably has come up before somewhere in geometry. And it's getting to be in the spirit of the isoparametric inequality. And the proof of it uses the idea, Fleming's idea, the proof of their isoparametric inequality. Yeah? Closed. It is a closed. It's SM. Yep. Thank you. Yeah. Yeah. It's an N form on SM. Cool. I wanted to check how I'm doing on time. Is anybody? So it is 12:08 now. I'm not sure when I started. A couple more minutes? OK. So I give a couple-minute summary of how to prove this. Proving this is similar, or this even follows from this. OK. So here's SM, and it bounds Bm plus 1. And inside of here, we choose a point P. So P is in, let's say, the 1/2 radius ball. All right. So if I take Bm plus 1 and I take away P, then I get something that's diffeomorphic to SM cross 0, 1. Right. It's called this diffeomorphism C sub P. And on SM cross 0, 1, there's an obvious projection to SM. So if I form omega here, I can lift it up to a form here. And then I can pull it back, and I get a nice closed form, which is defined outside of this point. So omega sub p is defined to be Cp star of pi star of omega. So it's a closed form outside of this point. Now this doesn't look that great because it's quite singular as we approach p. And we need to find a closed form. So omega p does agree with omega on the boundary, but it gets very singular near this point, and we need to find a closed form on the whole ball. Right. So one of Fleming's great ideas is that we can improve something like this a lot by averaging. So the Fleming averaging idea is to take omega bar and define it to be the average of omega p as p varies over this smaller ball. And then, even though each of these forms is singular, this averaged form is not singular. It's even C1 alpha for a small alpha, and it's closed, and it has the right boundary data, and it has the right bounds. So let me just quickly indicate why this thing is at least bounded. So omega bar is C1 alpha, d omega bar is 0, and omega bar L infinity is not too much bigger than omega L infinity. So the idea is, if I take, let's just think about this. If I take omega bar at a point x, it's bounded by the average of omega p at x. And omega p of x blows up only when x is close to p. So omega p is quite nice out here. And as the point x gets close to p, omega p gets big. And it's not hard to work out the rate at which it gets big, which is the distance to the bad point to the negative n. So this is bounded by the average over the m plus 1 ball of x minus p to the negative n dp. And that's a convergent integral. So this is actually a nice bounded form. And a similar argument shows that its derivatives behave well. So it's a nice C1 form, and it's still closed. OK. Thanks for your attention.
OK. Any questions, comments?
Is it possible to sketch in a couple of words how this issue of another infinite homotopy group is dealt with?
Yeah, so the question is to sketch quickly how to deal with the second infinite homotopy group that comes up. I don't think I can do that, but I can try to say why it's harder. Yeah, so at first I thought we get up to the second step where there's an infinite homotopy group, and we need to define something like a wrapping number that says for each, so let's say we get to the 2n minus 1 faces. And so we have to have some wrapping number that describes the Hopf invariant of each 2n minus 1 face as it wraps around Sn. And then we should do something like this. It should be a cocycle, and we should do something like this. But if you look at the definition of the Hopf invariant, it's more complicated than the definition of the degree. And so this attempt to define a relative Hopf invariant is actually kind of tricky. And I believe that that's the thing that really makes it worse and that gives us the L squared. I think that's the best I can do in a few words.
Other questions?
Yeah.
If you replace Sn with some other manifold, do you still get polynomial bound under the case constant of the
Yeah, that's right. Yeah, so their work applies to a lot of spaces, x to y, and there's some dependence on x and y. So I'm not going to be able to say the precise thing, but it applies to many spaces.